So what is up, everybody? How are y'all?
Good.
Yeah. So this is the brave few who fought the cold. Awesome. All right. So today we're going to be talking more about limits, and then we're going to try to get into some continuity stuff. So let's say we're given a function that looks something like this. We want to know what the limit as x approaches 0 is. Any ideas on what our first step might be? Those of y'all at home, any thoughts on how to solve this? That sounds like a resounding no. So the first thing we're going to want to do is notice that we can multiply this thing by 1 and not change the thing, right? So why don't we pick a very particular one? Why don't we choose to multiply this by the square root of x plus 1 plus 1 over the square root of x plus 1 plus 1. This is 1 after all, right? Yeah. So let's multiply our problem. Square root of x plus 1 minus 1 over x. Limit as x goes to 0. When we do this, what's going to happen? Well, notice the top. The top is of a very particular form. Our numerator, because of the way we've got this set up, is of the form a minus b times a plus b, right? Agree? And this thing is going to come out to be a squared minus b squared, right? Well, here, our a is equal to the square root of x plus 1, and our b is equal to 1. So our numerator here, after we simplify this all, it's going to turn into something like this. The limit as x approaches 0 of square root of x plus 1, that thing squared, minus 1 squared over x times square root of x plus 1 plus 1. Everybody agree? So when we do the algebra here and work everything out, we're going to find that this comes out to be the limit as x goes to 0 of x plus 1 minus 1 over x times the square root of x plus 1 plus 1. Well, hey, we could drop those parentheses in the numerator. Yeah? When we do that, the ones are going to cancel. So we're left then with the limit as x goes to 0 of x divided by x times the quantity square root of x plus 1 plus 1. We can cancel these x's now. And when we do, we're going to get a limit as x goes to 0 of 1 over the square root of x plus 1, that quantity plus 1. But there's a catch here. This can take on a 0, right? This cannot. So we have to mark that somehow. We have to say, whenever x is not equal to 0, these two things are equal, right? Make sense what I mean? So we have to add that restriction into this. Now, we can apply that limit though, can't we? So what's that limit now? Yeah, just going to be 1, or 1/2. Because when 0, or when x approaches 0, this radical is going to approach 1, plus 1 is going to be 2, so we're going to get 1/2, right? So looking at the method, book says more or less the same thing, right? What we're doing is we're multiplying by this 1, and then we're canceling out those x's to get something that we can work with. What we do, we get this. Now, why does this work? After all, that first function and that last function, they're not equal, right? This is not equal to this, because this can't take on a 0, but this can. Why does this work? Any thoughts? Think about the last thing we were talking about last class. This works because of a thing called replacement theorem. Replacement theorem just tells us that we have these two functions that are equal everywhere except at one point. Then their limits are going to be equal. Make sense? And that's what we've done here, right? We've said our functions are equal everywhere except for at 0. So we can just go ahead and say, well, under the limit, these two things are going to be equal. In this limit, we can calculate directly. Everybody cool with that? So effectively, all we've done is we've plugged a hole. I don't have the graph of that. Did we go over this problem last class? I don't remember. I think we did, right? Yeah. The one right before it? Okay. Well, I'll let y'all work on this for a second. I want to see what y'all come up with on this problem. I don't have a plug in this classroom, so I'm going to give you all about 2 minutes to do it. So looking at this, what did y'all try first? Factoring. What's another method we might be able to apply here? Yeah, the long division, right? So just as something to review, let's look at what this long division would come out to be really quick. So we're going to divide by x plus 3. We're dividing x squared plus x minus 6. All right. What do we have to multiply x plus 3 by if we're going to get rid of that x squared? X, right. So multiplying x plus 3 by x, we're going to get x squared 3x. We're subtracting this, right? So the x squared is going to cancel. We're going to get negative 2x down here. We're going to bring down this negative 6. What do we have to multiply by now? Negative 2, right. That's going to give us negative 2x minus 6. So everything's going to cancel, right? So we can use log division here to find out that x squared plus x minus 6 over x plus 3 is equal to x minus 2 whenever x is not equal to negative 3. Is everybody with me so far? All right, so what we just found was an alternative equation we can plug in here, right? Like now we can just apply replacement theorem and get our answer. Because the limit's really easy to calculate on this thing. And this thing is equal to this everywhere except at negative 3. So the limits are going to come out to be equal, right? All right. So I'm going to say no, that gives us that the limit as x approaches negative 3 of x squared plus x minus 6 over x plus 3 is equal to the limit as x approaches negative 3 of x minus 2. Now, from those properties we were talking about yesterday, we know that this breaks up, right? Like what we're doing is we're applying the limit to all of this, but because of the properties of a limit, this comes out to be equal to the limit as x approaches negative 3 of x minus the limit as x approaches negative 3 of 2. Well, this is going to come out to be negative 3, and this is going to stay 2, right? So this is going to give us negative 3 minus 2, or just negative 5. Make sense? So what we're going to be doing here for a lot of these different problems is really just massaging the algebra. Simplifying as much as we can. Finding ways to get rid of these zeros in denominators, right? Like, it's really all we're doing here. When we do that, we'll get to these replacement equations and then be able to apply the limit. Everybody with me on this? So effectively, what we've done here is we've said, this is our original function. There's a hole where we're trying to calculate the limit at. Well, I don't know what that hole is supposed to represent. I can write a table and get an idea, but I'm not promised to get the right answer. There are cases where we wouldn't. So the next best thing is to simplify our problem and find a replacement. And a replacement will plug that hole. And again, same idea. They use the factoring method, which is actually a lot faster than what I did. I just wanted to review the long division rule. Once they factored it, they simplified it, they just applied direct substitution. Same idea. The reason why I wanted to review this long division was because of problems like this. That problem that I asked y'all to work on for a little bit and took forever because it's just a beast, that would be really quick with long division. Having said that, remember last class I was talking about the limit from two different sides, two different directions? That's because built into the limit, there's actually two other limits. Talking about a pain in the ass, right? Limits inside of limits, like limitception. Bro, I'm killing it. I'm like the Bill Murray of the math department, all right? Y'all can laugh. All right, so what the limit in terms of one side is really just that. It's saying, if I were to approach this thing, I'm not actually going to run across the class, and that would be too much. But if I were to approach this thing from one side, what's my limit? If I were to do it from the other side, what's my limit? We represent it with a negative or a positive sign to the right of that value that we're approaching, right? Of our what our x is approaching. Does this make sense? Yeah. If we use a negative sign, that means we're coming from the left. If we use a positive sign, it means we're coming from the right. Having said that, unfortunately, I don't have a good mnemonic for how to remember that. Because that is very much one of those niche things, right? Like, this is the type of thing we would all make a mistake on. So, whenever you see limit as x approaches some constant from the left from negative, this is from the left side. Whenever we see the limit as x approaches c positive, this is the right side. I guess you could think of it as you're positive, you're right. I don't know. It's the best mnemonic I could come up with. Now, in order for us to say a limit exists, if the limit as x approaches c of our function f of x is equal to L, if this is going to be true, then these two things have to also be equal to L, right? Another way of saying it is the only way for your limit to approach L is for your left and your right-sided limits to agree. Now let's think about this for a second. When I first introduced the limit last class, I showed a case and I said the limit does not exist. So if you look at this, the limit from the left, I'm saying from the left is -1. From the right is 1. They don't exist, or they don't agree. So a limit does not exist. So all this is saying is that they approach the same point. You don't have what's called a jump discontinuity. Anytime you see this Grand Canyon of numbers, this chasm between your limits occur, it means the limit doesn't exist. It means the limit from the left and the limit from the right don't agree. Everybody cool with that? So as another example of that, the function absolute value of 2x, that quantity divided by x, it leads to one of those chasms. So the limit's not going to exist here because coming from the left, we're going to get close to -2. Coming from the right, we're going to get close to 2. Make sense? And that's what we're saying here. Because the limit from the left and the limit from the right don't exist or don't agree. The limit doesn't exist. So reiterating, existence of a limit just requires that your limit from the left and the limit from the right are equivalent. Notice we haven't said anything about what it takes for the limit from the left to the limit from the right to exist. Really not going to. We just kind of are going to assume they always exist. There are cases where they're not going to, but we're not going to get into that. Having said that, why don't you all try this problem? The graph of this will look something like this. thinks they got the answer? Anybody at home think they got the answer?
No.
Is anybody at home watching?
Yes.
I am.
Awesome. All right. So what we're going to do here is we're going to apply the limit from the left and we're going to apply the limit from the right, right? This is going to represent our left part. This is going to represent our right part. We're approaching one. Everybody agree? So what's the limit from the left? It's going to be 3, right? The limit from the right, it's also going to be 3, right? So we know the limit's going to exist, or at least we assume it does, because I haven't shown any of the math yet. So how does this work out? It works out like so. What we've got, okay, that hasn't migrated yet. Cool. What it's got, or what we've got, that we're just going to apply the limit to the 2 individual parts that represent our function from the left side and from the right side. When we apply it from the left side, all right, it comes out to be 3. When we apply it from the right side, it comes out to be 3. So our limit exists and it must be 3. Does this make sense to everybody? Yep. Now let's look at that graph. The more precisely drawn graph. This is that left side, right? This is that right side. Notice there's this inflection point, right? Or I mean, not this inflection point, this cusp. But both functions approach that same value. They would have that same value if they were allowed to exist at that point. And that's all we're saying here. So really, one way to think of the limit is, it answers the question, if the function was allowed to exist on this part of our real number line, if this number was in our domain, what would our function be? Another way of saying that is, the domain of this function negative infinity to 1 union with 1 to infinity, right? So 1's not in our domain, so our function can't take on that value. But if it could take on that value, what would our function be? Does that make sense? Having said that, the other catch to this is when our one-sided limits don't agree, what our limit's telling us is we simply don't know what it would be because you have 2 different choices. Does that make sense? Cool. Having said that, as another example, we have what's called a stepwise function. A stepwise function is just going to be a function that looks like stair steps. It's going to look something like this. Mathematicians have great imaginations, so we call them step functions. Looking at this graph, what do you think the limit's going to be? Well, all right, the question already tells you it doesn't exist. How do you think we're going to show it? Like, what do you think is going to be done to show that the limit doesn't exist as 2 approaches 2? Or I mean, as x approaches 2. Well, we're going to find the part of the problem that 2 is in the domain of, right? That means this part, and possibly within the limit, this part, right? So 2 up here is going to be applied, or the limit is going to be applied to a constant. And then down here, the limit is going to be applied to another constant. So what we're going to find is that we approach 2 different constants. So what I am saying is what our question is asking us to do is to find the limit as we approach this value 2 here. But if you notice, coming from the right, as we approach 2, we're going to approach 16. Coming from the left, as we approach 2, we're going to approach 14. Yeah? And that's what happens. So because the two-sided limits, the 2 different sides of a limit don't agree, the limit does not exist. Okay. What about here? What's going to happen here? Who's seen Mean Girls? Okay. So what does Lindsay Lohan say about the limit as x approaches 0 of 1 over x? Doesn't exist. Well, same thing's going to happen here. It's not going to exist, right? We're going to approach 0, 3 over 0, right? Okay. How do we know it doesn't exist? What does it look like? What is this thing doing? Well, let's graph it really quick. Our function is going to look something like this. So as we approach two from the left, from the right, what is our function approach? Infinity. So we just go up forever, right? We're not approaching any one number, we're approaching every number bigger than our previous number. So it's going to be infinity. And from the left, what is it going to be? Yeah, negative infinity. This is what's called an unbounded function. It's unbounded because, well, you can't really put a bound on infinity. Like, you're not going to lasso that into something nice to work with, right? Does this make sense to everyone? Yeah. So having said that, welcome to your world of infinities. These are going to be things we're going to start seeing show up here. Just a fun fact about infinity. There are actually 2 different types of infinity. There's what's called the countable infinity, and that's what you can count to. 1, 2, 3, up to infinity. And there's what's called the uncountable infinity, and that's the number of numbers that exist between 0 and 1. Because there's no way to count all of those numbers, right? But yeah, just a fun fact about math. So, having said all of this, comment on notation. Whenever you see this arrow, we're saying f of x approaches infinity as x approaches 2 from the right. Makes sense? So, at some point when y'all get home this weekend, I'd like you all to look back over this concept text slide and just quiz yourself. See if you do understand it. See what questions you need to ask. Having said that, what time is it? It is 9. Class ends in what, 12 minutes? I know, right? Yes, we're almost done. But before we're done, let's talk about continuity. What do you think continuity is? Based on everything we've talked about, what do you think continuity is? Well, the word comes from continuous, right? So if I say something is continuous, a function is continuous, what might I mean? There's no holes in it, right? Now, there's no breaks in it, no jumps, no point that all of a sudden jumps off of our graph. So there's nothing like, this was slide 69, and we are going to, way too far. So there's nothing like this, where there's a hole. There's nothing like this, where there's a huge break. There's nothing like this, where that point randomly jumps off your graph. This is what continuity is about. It's about this thought of, is your function continuous or not? Can you draw the graph of it without lifting up your pen or pencil? Having said that, there are 3 conditions that you need to satisfy in order for your function to be continuous at a point. Your function at that point has to be defined. The limit at that point has to exist. And the limit at that point has to be equal to whatever your function at that point is. So this answers all 3 of those conditions, right? Agreed? So like I said, we can think of the idea of continuity as being able to draw your function, the graph of your function, without ever having to look it up. As a quick example, we've got 3 different types of discontinuities. We've got just that missing point. We've got that jump discontinuity. We've got that misplaced point sort of thing happening, right? Notice when we talk about discontinuity, we're talking about at points. But when we talk about continuity, we talk about it on intervals. So in this case, we would say this graph is continuous, or this function is continuous between A and C, including A, not including C. This graph is continuous, not including C, up to C2. This graph is continuous between C2 and C3. Between C3 and including B. So we talk about discontinuities at points, but continuity on intervals. Make sense? It's kind of like breaking noodles. The noodle is broken in half. It's broken at a point, but it's not broken for those other two pieces, right? Same idea. Having said that, polynomials, continuous everywhere. Rational numbers, rational functions, only where your function's domain exists. So this is an example of a rational function, right? 2 is not in our domain. And it happens to be where our break is, but we're continuous everywhere else. Make sense what I mean? Having said that, and to beat a horse to death, are these functions continuous, yes or no? I hear nodding. Well, I see nodding, but I don't hear anything. I'm assuming that means we agree these functions are going to be continuous because they're polynomials, right? Right. So since they're polynomials, we're good to go. And we can see that if we were to graph them, right? Okay. What about these? They're rational functions, so we know they're not going to be continuous everywhere, right? Where's A not continuous? At 0, right. Our first function here can't be continuous at 0. What about our second one? 1, right. Our third one? Yeah. Let's see. Let's look at that graph. Knowing what the graph of this is, does that help? A little bit, right? In this case, it's continuous everywhere. Because what does it take for our rational function, for a number not to be in our rational function? In the domain, I mean to say, of our rational function. In this case, it would take our domain, our denominator to be 0, right? Is there a real number that we can do that with? No. So we know all of the real numbers have to exist here, right? That they have to be in our domain because there's no real number we can plug into this denominator to make it 0. So since that's the case, they all must be there. So we know it's continuous from negative infinity to infinity. Make sense? So when looking at rational functions, the first thing you should ask yourself is, what numbers can make my denominator 0? I know those aren't going to be in my domain. Because I know those aren't going to be in my domain, I can start working on this. I can start doing things. I can start saying things like, for the graphic, I know I'm going to have some sort of discontinuity at these numbers not in my domain. Make sense? Having said that, I want to point out the variability between all of these. So 1 over x gives you this hockey puck looking thing, or this hockey stick looking thing, right? X squared minus 1 over x minus 1 gives you just a line with a hole in it. And then 1 over x squared plus 1 gives you this bell curve looking hill of a graph, right? So not all rational functions are going to look the same, right? And I want to point this out because polynomials, they generally have a form or two that you're going to work with. Rational functions, not so much. So having said that, we've already gone over those. How much time do I have left? 2 minutes. So since we only have 2 minutes, I'm going to go ahead and let y'all go. If you have any questions, I'll stick around for a couple minutes. But y'all ready to go. Another fun fact about math, the way we know that climate change is happening is based off of the greenhouse effect, right? That was mathematically proven 250 years ago by a guy named Joseph Fourier. He happened to be a member of Napoleon's government, actually. He was his head of science in Egypt or something like that.